So public means you can access it anywhere. You can access a field, or, well, you can access a class member anywhere. Private means you can access a class member only from within the class itself. Protected means you can access it within the class itself or children of the class. Okay, so protected exposes it to the children of the class. Why do we need these? Yeah, so we can keep people from directly accessing our, as we advertised it, mostly the fields, right? But from a method perspective, it also allows us to hide certain methods within the class and not make them public features of our object. Okay, so for instance, if we're thinking about this like a cell phone, maybe if you remove the battery, there's a little pin thing to do a factory reset on the phone or something like that. This wouldn't be, we'll call that kind of a private feature, something that's internally reserved for those in the know who have access to the internal parts of it, where it's not one of the publicly exposed interfaces of that of the phone. Make sense? But as we've advertised in it here, it's mostly for the fields, so that we don't have direct access to change the variables associated with a class, or at the very least, we make them go through the process of calling a method. What are those methods called? What's the method? What are the methods called that give us access to private members? Setters and getters. Setters let us set it. Getters let us get it. Okay. What's the old school name for the same things? Accessors and mutators. Okay. Let's start talking about data structures. So data structures are structures for holding data. So descriptive, right? Well, up to this point, even as we've been talking about fractions, by this definition, a fraction object is a data structure. Okay, that is, it is an object that we created that can hold some pieces of information. Specifically, it held numerators and denominators associated with something that commonly we know as a fraction. And then it added some abilities for us to do stuff with fractions. Okay, so by definition, our fraction object would be a data structure. Now, what's different between the generic phrase data structure and our fraction class is our fraction class solves a very specific problem. What we're going to be talking about here in terms of data structures is a collection of generic data structures that expand the capabilities of a programming language to allow us to solve larger general classifications of problems. Okay, so most of these happen to be, at least initially, they happen to be ways of storing things like arrays store things. Okay, arrays are collections of like data. Okay, but arrays have some weaknesses. So the very first data structure we're going to look at is something called a linked list. All right, so I'll bounce back to data structures here in a minute, but first, let's talk about the problems with arrays. Remind me, what's an array? Go ahead. Okay, that's how they're implemented. So arrays are implemented when you define an array, it must grab a collection of memory that is contiguous right next to each other in memory. What are arrays for? Similar elements, same type elements, something like that. So we can create an array capable of holding 10 integers, for example, right? Under one variable name. So if we need to hold a collection of numbers, we might create an array and fill it up with some variables. So quick reminder here. Let's see, we'll just use driver. So if I want to create an integer array called AR, and I want this guy to be able to hold 10 integers, and we'll go ahead and put some random integers in there. How many elements are in AR? How many elements are in AR? Go ahead. Huh? You said 10 again? No. How many elements are in AR? AR, not length. AR.length, number of elements. In this particular example, there's 10. Okay, but if I change that to 100, we don't want to have to rewrite large portions of our code. Okay, so AR.length. That's why it didn't auto self-finish, right? Okay. So AR.length is the number of elements in AR. Okay, now we've learned a little bit more here. So what kind of animal is length there? Cat, dog, method, field. Field? Class field or instance field? Instance field, how do you know? Using instance to call it. Okay, how do you know that's a field? No parentheses. Methods have parentheses. Even if it's an empty parameter list, it has the opening and closing parentheses. So if it was a method, it looked like that. Like the string's length. Okay, so when we get the length of a string, it happens to be a length method. The length of a array is a field. Now arrays are kind of defined to be special. Let me go ahead and import java.util here for our random class. So for instance, I can say system.out.println ar.length. And that's going to display a 10 for me in this particular example. Can I say ar.length is equal to 5? Okay, an interesting additional protection thing we can do. That is, we have a modifier called final, which means it cannot be changed. All right, so if we go back to our security settings, these guys, we could say there's a setting called final, which allows us to create a variable, set it, and it automatically would have read access, provided we made it public or something like that. So final is not a replacement for public, private, or protected. It's an additive. All right? But by making it final, we essentially make it read-only. You could not write to it. All right? Not something you'll probably use that often. It's very situational. But in this case, they made this field length a final field. So when this array was first created right here, they set length equal to 10, and that's it. That's done. Okay? And that kind of goes with what we're going to talk about today. So they made that final. We can access the length right here. We can read it, but we cannot change it because it's final. Make sense? All right. Now, why did they implement it as a final field rather than a private field with accessor methods, with a getter and a setter? Well, at least a getter. Go ahead.
Because the array will never be anything but 10.
Yeah, that's it. So when we get back to this slide over here where I'm asking problems with arrays. When we initially build an array and we tell it its size, that's its size forever. Okay? And that kind of goes with what Randy was saying with, when we requested our real estate agent here, the new keyword, went out and found us enough memory in a row, contiguous memory. And that would be a good quiz question sometime. What does contiguous memory mean? Something like that. Hint, hint. Okay? Yeah, memory in a row. Okay, so it went out and got us enough contiguous memory to hold this many of these guys. That many ints. Okay? How big is an int in Java? 32 bits, 4 bytes. Those are synonyms for each other. So we need 40 bytes of memory in a row, or 320 bits of memory in a row. And that's what gets stored in AR. AR is a pointer, right? What's a pointer? Primitive type variable capable of holding a memory address. So AR is a variable, and its value is a pointer, which points to the contiguous memory where our 10 integers live. Okay, so as you pointed out, this guy will never be anything but size 10. Therefore, they made this field a final field, allowing us access to it without writing a method. We can acquire the length of it, okay? But we can't set the length of it. The length of it was set once and only once when we first built it. Make sense? Now, the alternative is, we talked about strings just a second ago, or a minute ago, whatever it was. Strings offer a length method. Okay, so that must mean that the length field of the string, assuming they named it length, must be have what kind of security setting? Public, private, or protected? You can rule one out right off the bat. It's not public, right? We can't directly access the length of a string. We can't say s.length, no parentheses. Can't say that. Okay? It's at least protected. That's if there's classes that inherit from string. It's not public. Instead, what have they done? Let's just assume it's private for this argument. Instead, what they've done is they've given us a getter method called length that returns the current length of the string. And why did they choose to do that? Because strings can change their length, right? We can concatenate values, concatenate things onto a string. We can set a string equal to a new string, that kind of stuff. So strings their length is modifiable. Therefore, rather than making it a final field, which wouldn't allow us to change it, it's a private field that they give us access, read-only access to through a getter. That makes sense why they made those decisions? Now, would it have killed anybody for them to create the length field of AR, of arrays, to make that private and then just give us a getter method for getting the length? It would have still worked, right? Could have still gotten the length of an array. But it probably, from an object-oriented perspective, makes more sense to make it final, because when somebody's looking at your code, you can look at it and say, oh, this value is final. It will not change. So it's a variable in name only, even though I know now it will not vary. Make sense? Okay, so kind of a design decision. You kind of get into the mind of the folks who wrote Java a little bit with that, so it gives us an interesting example. Okay. So we created an array capable of holding 10 numbers. We went ahead and created our instance of the random class that we're just going to use to fill our array up with some random values. We'll create a loop that spins through bucket 0 through bucket AR.length -1, the legal buckets in AR. So in this case, AR has 10 buckets in it. Legal buckets are 0 to 9. And each bucket will say AR at bucket I is equal to R.nextInt. And well, I don't know, that'll give us a number between 0 and 9. We'll add 1 to it, 1 to 10. Okay, so R.nextInt, when we pass it a integer as part of the parameter, there's multiple versions of nextInt. This particular version of nextInt takes an int as a parameter. It returns a value between 0 and this number -1. By adding a 1 to it, I get a 1 to that number, 1 to 10. So I'll go ahead and fill my array up with that. Then we'll have a second little loop that'll do the same thing. We could have done it all in the same loop, but why not?
So what's nextInt's relation to random?
It gets the next integer. It gets us the next random integer. So if I come in here and I say R.nextInt, so we have two versions of it. one that takes no parameters. This one returns a random integer in the range of all integers. What's the range of all integers? What's the smallest integer? What's the largest possible integer? That was a weird twitch thing that happens when students say something stupid. What's the range of all integers?
Plus minus 2 billion.
Plus or minus 2 billion. Yep. Randy pointed out, I think it was, you pointed out it was 32 bits, right? Okay, so integer is 32 bits, 4 bytes. So that means integers are plus or minus 2 to the 31st power because they are signed. They hold negative numbers to positive numbers. So the smallest integer in the range of all integers is about negative 2 billion. The largest integer in the range of all integers is positive 2 billion and some change, right? Okay, so calling r.nextInt like that will return some value between negative 2 billion and positive 2 billion. That's what that guy will do. Okay, and I can whittle that down if I want, but there's a second version of nextInt that takes an integer as a parameter. And that guy returns a value between 0 and n minus 1, where n is the integer you pass in. So it's 0 to that value non-inclusive. So if I pass in a 10, it'll give me a number 0 to 9. I'm then adding a 1 to whatever that number is, guaranteeing me a number between 1 and 10. That make sense? Okay. What's this an example of right here? Polymorphism. More than one method with the same name with a different number and or type of parameters. I was expecting my little mantra. All right. What was I talking about? Oh, so this loop goes through and fills it up with random numbers between 1 and 10. And then this loop, which is the identical loop, because this is our loop pattern for spinning through every bucket of an array. This loop goes through and just prints out every element of that array to the screen. We could have done both of these inside the same loop by just taking this line and putting it right after this one, but what the heck. So we should get 10 numbers between 1 and 10. Fair enough? All right, so that's a refresher on what arrays are. So now the slide we're currently building is problems with arrays. So what are some of the problems that we know of with arrays?
You have to set the, like, how big it is, even if you don't know how big it's going to be.
Fixed size. Yep. So they are a fixed size. We have to set that array to be a certain size right when we create it. And if we don't know how many things we need to hold, we got a couple of options. We can just make it hold a whole bunch of things and hope that's enough. Okay? Or we can make it hold a minimum number of things, and then every single time we need to hold something more, what do we need to do? We have to create a brand new array. Remember from last semester, our example was something along the lines of, let's say you have a house, and you decide you want to add a porch to the house. Well, the array version of that is you knock down the old house and build a new house that also has a porch. Now you want to add another bedroom. You knock down the house that you've already added the porch to, build a new house that has the porch and also another bedroom. Not very efficient or cost effective for that matter, right? That's the array version of doing things. So that kind of goes hand in hand with what he said about, fixed size. Make it as big as you think it has to be to solve the problem you're solving. So in that case, if we think we're only going to hold 50 pieces of information, but we might need to hold more, well, maybe is overkill. We might say, okay, we'll create an array that could hold 1,000 things. And maybe we ever hold 60 things. Well, we just are, let's say 100 things. That way the math's easier for me. Okay? That means we have 900 buckets that were wasted. If they're integers, that's 900 times size of int, which is 4 bytes. Now we've wasted some memory, right? Okay, so problems with arrays, we have a fixed size, so memory may be wasted in the event that we create an array larger than we think we might need. Kind of to cover our butts, to avoid this idea of knocking down the house and building another one with a porch. Any other problems with arrays? That's our big one, right? They're fixed size.
It needs to be contiguous.
Okay.
I don't know if that's
Is that a problem?
only if it's really big, but
Okay.
that
Well,
deals with fixed size.
sure. Let's jump to the next slide, the good things about arrays. Problems with arrays, benefits of array. Arrays, good stuff. KK, thanks. Okay, what's good about arrays? Fast. Yeah, they're fast. Fast. Because memory is contiguous. So that idea of contiguous memory really lends itself to why they're fast. Because each bucket of the array can be computed. Okay, what I mean by that, if I say AR at bucket 0 or AR at bucket 3, AR at bucket 0 says go to memory address AR, then add to it 0 times, if we're dealing with an integer array, size of int. This guy down here says go to memory address AR, add to that 3 times size of int. So if we assume AR was at memory address 100 and size of int is 4 for bytes, this guy would boil down to 100. This guy would boil down to 112. That means the value at bucket 0 lives at memory address 100. The value at bucket 3 lives at memory address 112. We're able to compute those memory addresses because the memory is contiguous, right in a row. We have numbers, the bucket 0 is here, bucket 1's here, bucket 2's here, bucket 3's here. Make sense? So arrays are fast because of the contiguous memory. Now, going off what he was saying, we could throw contiguous memory as being one of the problems with arrays. And I think it's fair because it kind of segues into what we're going to be talking about today. So we'll put contiguous memory as a possible problem. That is, we require that we have enough memory in a row to hold the elements of the array. So if you're going to create a really, really big array, let's say it's going to hold 2 billion integers. Well, now you're starting to talk about a legitimate large amount of memory, right? And now you have to have enough memory in a row to hold 2 billion times size of 4. Size of integer, which is 4 bytes. So 8 billion bytes. So how do I write 8 billion? That's 800,000, 8 million, 80 million, 800 million, 8 billion. So that's bytes divided by 1024 is kilobytes, divided by 1024 is megabytes, divided by 1024 is gigabytes. So that means I would need 7.5 almost gigabytes of memory in a row in order to hold 2 billion integers. How many of you in here only have 8 gigabytes of RAM in your computer? Okay, so loading the operating system in RAM's probably out. So good luck running your computer without an operating system. But we can certainly see where this starts becoming an issue, right? Not only do we need this much free memory to hold that many numbers, we also need it in a row. That makes the problem that much harder, right? Okay, so I think it's fair to say that contiguous memory is also one of the negative aspects of an array. but certainly it's a positive from the perspective of it being fast. Okay. So arrays have their purpose if we know how much data we're going to hold. So if we know we're going to hold 10 things or 100 things or 150 things, we know that to start with. And the number of things we're holding isn't ridiculous in size to the point where we don't feel like we're going to have major issues with finding enough memory in a row to hold it. Then an array is the correct solution. It's the right tool for the job. So one thing I want to emphasize here is, even though we're going to talk about something new today, it's not an upgrade to arrays. It's an alternate tool. Okay? Sometimes arrays are the appropriate size. In fact, I would say if you are going to hold 10 things and you know exactly it's going to be 10 things, an array is always better than a linked list. Because we like things to be fast, right? And we know how many things we're going to hold. And 10 is not a ridiculous number of things. We got enough memory in our computer. Well, that's probably not going to be a problem, right? Array is the right tool for the job. Now, we're going to be looking at our first data structure in here, something called a linked list. A linked list is a collection of what are usually known as nodes. So we can think of these as being the equivalent of buckets in an array. So each node holds one value, just like each bucket of an array holds one value. So a linked list is a collection of nodes. I might even say node objects that are linked together by a pointer to the next node object. Okay, to give you a visual of this, we're going to do a list of some random numbers between 1 and 10. So I'm going to create, our first number will be a 3. So this box here represents our node. So I have a node called 3, or a node that holds the value 3. Now, when I first started this linked list, I didn't know how many values I was going to hold. Okay, so initially, I have a little variable, typically called head. And head is a pointer that points to the head of the list, or the very first element of the list. So when I first brought this linked list into existence, it was the empty list. That is, head pointed to nothing. Make sense? Then when I added my first element, so let's say we're always adding on to the end of the list. The end of the list is right here. So that means I made head point to my new node. Now my new node also contains a pointer, which points to the next dude in the list. And right now, there isn't another dude in the list, right? So I'm going to go ahead and create another node. This one's going to be a 7. And we'll add them to our list. I'll create another node. This one's going to be a 4. We'll add them to our list. Now, this node right here lives in memory somewhere. This node right here lives in memory somewhere. This node right here lives in memory somewhere. It's just like we created our multiple instances of fraction and each one had its own memory address. That was not necessarily right next to the one before it. So in this case, we have this memory address, which has a pointer, which points to here. So instead of a numerator and a denominator, a node has a next node pointer. That is a variable that holds the address of the node that comes after that guy. So this guy's at a different memory address, probably not right next to this guy. And then I've really shown that through my picture here by this third guy here is somewhere else in memory. Way off somewhere in memory. But I can still get to him by using the pointer from this node to get to this guy. All right, so maybe my linked list looks like this initially in our picture. If I want to get to the value 4, I can't just go right to 4. I can't calculate it like I could with arrays. Okay? Why? Because the memory is not contiguous. These guys are not sitting right next to each other in memory. Instead, what I have to do is I have to go to the front of the list. Let's say I happen to know this guy's the 3rd element in my list. I would go to the front of the list, go to element at bucket 0, then follow his next pointer to bucket 1, follow this next pointer to bucket 2 to get to this element. That make sense? So I have to traverse the list.
So is that slow?
Slow. Yep. So we want to think of linked lists as being relatively slow compared to arrays. We can't just jump to a certain part of a linked list. We have to start at the beginning of the linked list, as we know now. There's actually versions where you can also keep track of the end of the list and walk from the end towards the front. But generally speaking, you have to traverse the list in some direction. So it's relatively slow compared to arrays, since arrays are computed. But they are very memory efficient. We created an initial linked list that has nothing in it. That's good, because I haven't stored anything yet. Then if we want to add an element, we don't have to knock down the house to build the porch. We just build the porch. If we add another room, you add another room. Make sense? So it's memory efficient because it does not require us to have all the nodes sitting right next to each other in contiguous memory. We could just put, we only have to have an open space of memory big enough to hold a single node in order to add something to our list. So when I added this 4, I only had to have a piece of memory big enough to hold this node, and then I just told this guy where to find the guy that comes after him. Okay? So again, linked lists are not an upgrade to arrays. It's an alternate tool. They are slower than arrays, but they're more memory efficient than arrays. Okay? Arrays are always the right tool if we know how many elements we're going to hold and it's not a ridiculously huge number of elements. Arrays are always better in that case. But if we don't know how many elements we're going to hold, a linked list is almost always better. We're giving up a little bit of speed, but it allows us not have to keep knocking down the house every single time we want to add an element. All right, make sense? So, let's build us a linked list. So if we're going to design this, our linked list object is going to keep track of a node pointer called head, at the very least. Right? It's got to know where the head of the list is. It's also going to have a constructor that probably takes no parameters and makes head point to null. Because the initial, we'll say, emulating the empty list. The initial state of a linked list, that is a list that has nothing in it, is a linked list that has a head pointer that points to nothing. Make sense? We're also going to write a void display method which displays the contents of the list. So that's what our linked list is going to have in it. We're creating a simple linked list. All right, now, back here in our linked list, we mentioned this idea of a node. So if that's going to be one of our players, if you remember way back to 200, we called them actors, right? These guys are required to play this little game. So we're going to have to create a node object. And a node object is going to have a node next node field to keep track of who comes after this node in the list. Okay, it will also have, let's just say, by our example, we're creating a linked list of integers. So it's going to have an integer payload, which holds the actual value of this node. That's like the bucket of our array. That's the actual value the node holds. Go ahead.
So are we constructing this linked list, like making methods for it all, and what we're making total is going to be a linked list? Like
Correct. Yeah, we're building our own objects that will ultimately produce this linked list data structure, which is one of our generic data structures. Now, Java does have linked lists built into the language, but you're not allowed to use it yet. You have to write your own. You'll appreciate it more later. Okay, so it'll have a payload. Let's leave it at that for right now. Okay, we'll probably add a well, here, we'll just do this. Payload is probably going to be private, right? We want to make our fields as private as possible. Next node will also be private. We don't want to allow external entities to directly change those. All right, so that means that we probably then need setters and getters potentially. Make sense? So let's put that at our high level design here. Similarly, at our linked list level, our head node is probably also going to be private. We only need to know about that in the within the linked list class. And I actually had a little mistake here. The constructor for linked list isn't node, it's linked list. Okay. So now we've kind of designed the initial version of our linked list. So we're going to go ahead, come into Eclipse, and we're going to create these couple of objects. So just to keep things relatively clean here, I'm going to go ahead and delete dumb fraction and fraction. We don't need those anymore. And I'll go ahead and create a new class. And we'll go ahead and make nodes first, since linked lists are done in terms of nodes. All right, so we'll make the node class. And we decided that our node class is going to have a private node next node, and it'll have a private int payload. Those are the two pieces of information a node object will hold. Make sense? Now, the constructor for node, which I don't know if we designed that. Here's node. Let's throw our constructor in here. The node constructor is probably going to take in a payload, an integer. This will set this node's payload equal to payload and initially set the next pointer to null. When a node first comes into existence, it will have a value. So let's say I'm making a brand new node. This guy right here. This guy's going to be a 5. So brand new node, he has a value, but his next node doesn't necessarily point anywhere right now. So we initialize it to null. At a later point in time, though, we could make him point here and make this guy point here. And now we just added something to the list. We added something to the list in the middle. That make sense? And we'll talk about that more, but
Do you go back to that last slide?
Nope.
No?
Mm-mm.
Shucks.
Shucks? Who says shucks?
I do. How old are you?
Which one do you want to see? This one or this one?
Yeah, that one.
This one? This one?
Take your pick.
You want node or you want linked list? Or you like them both? Now, do you need to see this one? You're good at this one. All right. So our node is going to have, our next node is going to have a payload. We've made both of these private. We'll go ahead and make our constructor for node public. This guy will take in a payload as a parameter. And we'll set this dot payload equal to whatever payload was passed in. And we'll set this dot next node equal to null. Next node would have already had a default value of null, but I never like trusting that. It's bad programming practice. So if you want it to be null, set it to null. Make sense? Similarly, we probably want to allow people to get our payload, but not set our payload. At least not yet. But we might want to get at the payload. We might also want to be able to set the next node. But I'm not going to do anything at this point. I like software to kind of grow as we need it to, so I'll add features as we need those features, rather than try to over-design and solve all the world's problems day one. All right, so we're going to leave node at this point for right now. And now we're going to add another class called LinkedList. Okay, the LinkedList class is going to have a private node head. Then we're going to have a public constructor that sets this dot head equal to null. When a linked list first comes into existence, it doesn't have any values in it, right? And then we decided we'd make a display method. And we'll go ahead and fill in the display method a little bit for our starting point. If head is equal to null, system.out.println empty list. Okay, so when we initially create a linked list, the head pointer gets set to null. Then if we were to call the display method on that guy, it's going to ask the question, is head currently null? If it is, it's going to say, you have a list, but it's the empty list. That make sense? So we've kind of set up our skeletal structure for our linked list here in terms of linked lists and nodes. So we'll go out here to driver. We'll go ahead and create an instance of our linked list. Ooh, not typing so hot today. All right, linked list LL equals new linked list. So that's going to call upon our constructor right here for linked list that takes no parameters. And notice that when I called upon that constructor, I passed it no parameters. And what's this constructor going to do? It's just going to set this particular instance of linked lists head variable, which is a node pointer, equal to null. And then finally, just to test what we've written so far, I'll say ll.display, which should show what? Empty list. All right, so there's our empty list. And of course, that is the entirety of what linked lists do. We create them solely for the purpose of displaying the word empty list, or the phrase empty list. And we never can add stuff to them. No problem. We got this. All right, so now we might want to start adding crap to our list, right? All right, so we're going to go ahead and we want to, let me drag my Legos over here to the side. All right, so this is my list right now. So if we want to really connect our dots. This is LL. So LL is the name of my list, and it encompasses a single field called head. Make sense? And right now, head points to nothing. So it's null. So when I call the display method, it detects that head is equal to null, so it spits out empty list. Now, we might want to add a node to the end of our list. The point of having a list is to store stuff, right? All right, so go back into our design quickly. So what we'll do is in LinkedList, we're going to add a method, void add end. End. Add end. Void add end. And we're going to make this guy take in a payload or a value, whatever you want to call it. All right? And by add end, I mean we are going to add a new value to the end of our list. That make sense? So this adds a new node to the end of this linked list. That's what the add end method will do. So we'll go into linked list. We'll go ahead and write our method, public void add end. This guy will take in an int payload as a parameter. And right off the bat, if we're adding something to our list, what kinds of animals get added to linked lists?
Pointer.
What's that guy? What's the most generic way of describing that guy? It's a node. So we add nodes to the end of lists, right? So in order to add a node to the end of the list, we must first build a node. Fair enough? Okay. So I need to build a node in this case, and that holds whatever value is passed in for payload. So very first thing I'm going to say is node n is equal to new node payload. That's going to create us a brand new node object. And just as a reminder, what just happened? Well, let's go look at node. The constructor for node takes in that payload, takes in an integer. It sets this particular node's payload equal to whatever was passed in. And then it also sets this particular node's next node to null. So we create a brand new node, it has a value, and it points to nowhere. That's what it means for a node to be born, brought into existence. Okay? So, very first thing we do, we create a node. Now we'd like to do something with this node. What do we want to do? Well, we'd like to add it to the end of our list. So the next thing we need to figure out is where is the end of our list? The good news for us right now is that our list is empty. How do we know that? Well, we have to ask the question, but we'll say if this dot head is equal to null, that means if we're dealing with the empty list, right? That means that we can just add this guy to the front of the list. So the front of the list and the end of the list are the same. So we'll say this dot head is equal to n. Make sense? So if we're drawing that picture, if this is the current state of my list right here, and I just created this brand new node right here, and I notice that head points to null, all I need to do to add this guy to my list is set head equal to n. Make it point to my new node. So now that's the state of my list. That make sense? That was the easy version of adding to the end. Now let's add another node. Okay, so we'll add, because we haven't quite finished writing add end yet. This only works the very first time we call add end, as is. After that, we don't add anything, as it's currently written. So, let's say we want to make, I need to organize my Legos better. All right, so now we want to add 7 to the end of our list. So we're going to create our node that contains a 7. Did that. That part's the same, right? All right, now we want to add this to the end of our list. So we're going to ask the question, same question we asked before, is head equal to null? It's not. Head points to a node already. So since head's not equal to null, now we have to traverse the list to find out where the end of the list is. Make sense? How do we do that? Well, we need to start with head and keep walking from node to node to node until we finally hit a node whose next node is null. Okay? So does that mean that I can just say, okay, well, head currently points to here, and so this guy's not null, so let's just make head point here? We probably don't want to lose the front of the list. Okay, so never change the value of head, unless you're adding something to the front of the list, in which case you're updating the value of head. So what we're going to need to do is we need to create a second pointer. Usually this guy's called curnode. It's a reasonable name for this variable. And this guy will start off at the front of the list. And it will keep walking the list until we finally hit a node whose next node is null. If we have a node whose next node is null, what could you say about that particular node? If curnode is currently pointing at a node whose next node is null, what is true about that particular node?
It's the last node in the
It's
list.
at the end of the list. It's the last node in the list. Okay? And if we're adding stuff to the end, where do we want to add our new node?
It's the end of the list.
Right after this guy. If I'm currently staring at the last node and I'm adding another node to the end, I want my new node to go right after this node. Current last node. Make sense? So we need to write some code. We'll do an else here. So if it wasn't trivially the empty list, we need to find the last node in the list. That's what we need to do in this else first. So we'll create a node, curnode, and we'll start this guy off at, well, I like to say this dot head, but it won't make a difference. Start this guy off at the front of the list. Okay? Then we're going to say while curnode, which is right now curnode points to the exact same place as head points to. So in our current example, curnode and head are synonyms for this particular node. They point there. Okay? I want to ask about curnode's next node. Because I want to ask, is curnode's next node equal to null? If it is, I'm done, because I'm at the end of the list. If it's not, I need to traverse another node. How do I ask a node to inform me about his next node? Go into the node class here, because head and curnode both point to nodes, which is this kind of animal. How do I ask something of this type to tell me about his next node? I want you to read the code. I'm not asking you to dig something out of your head. This is what we've written so far. If I have an instance of node, how can I ask that instance to let me know who his next node is?
Use a getter.
Okay? As of right now, we can't. Right? As of right now, we can't. So we need to provide ourselves with a getter. Why is that? Somebody else other than him. At this point, he's less stupid than some of you. It's private. Next node is private. What does it mean for it to be private? Okay, fair enough. You can only access it in this class. So it can't be accessed in other classes. Okay? So we can only get at next node within the node class because we made it private. We need access to it in the LinkedLists class. So to solve this problem, well, we either make this guy public, which has its own problems, right? Because then we can have people changing the next node directly. Or, as he suggested, we create a getter. All right. So a getter would just be a method that returns the value of next node. So I can write it myself. I can say public int get next node, and this guy would return this dot next node. Oh, actually, interesting. It's not an int, it's a node. So next node is a node. So my get next node is going to return a node for me. So I'll return this dot next node. So I could write that myself if I'd like, or if I want to use Eclipse, I can just right click and go down to source and go to generate setters and getters, and setters, and we'll go to next node here, and we say we just want to get a getter, get next node, and we can choose how we want it to be, what the access modifier. We want this to be public. Okay, so we've provided read-only access to our next node now. That makes sense? So, little convenience that Eclipse gives us. But notice this is the exact same thing I just wrote, except I said this dot next node. Just because when I'm teaching classes, I like to be verbose. When you stop using this dot, you'll know why you stopped using this dot. So here there we go. All right, so now we've added a new feature onto our node class that allows it to expose for us for read-only purposes its next node. So I can come back to LinkedLists, and while I'm trying to find the last node, I can say while cur node dot get next node is not equal to null. While cur node dot get next node is not equal to null, I want to traverse. I want to set cur node equal to his own next node to make him move down the list so I can check the next node to see if his next node is null. Keep walking the list, walking the list, walking the list. So I'll say cur node is equal to cur node dot get next node. That traverses the list. After this while loop is done, cur node will point to the very last node in the list. That make sense? Point to the very last node in the list. And what do I want to do? I want to set that last node's next node equal to n. I want to add a new node on. So if the new node that I'm trying to build here is, so I just built, n holds this guy. That's my new node I built. Now I need to go figure out where in the list I'm adding him. So cur node starts at head, which happens to be the last node in this particular list. So I traverse a list. The while loop doesn't even run once because we failed the very first time because cur node currently points to a node whose next node is null. And then I say, oh, okay, well, I know which node I'm adding the new node after. So now I need to actually add this node after cur node. So that means I need to set the next node. That makes sense? I have not given myself that ability yet. I gave myself the ability to get the next node, but not the ability to set the next node. So I need to add that ability now to node. So we'll go into node. We'll generate setters and getters. For next node, I'm going to go ahead and set next node. So it gives us a setter. Hit OK. And there's our setter. So this now gives me a public function that I can pass a new node to, and this function will set this particular instance of node's next node equal to the node I passed in, a pointer to it. All right. So I'll go into driver. I'll go into linked list. and I'll say curnode.set next node to n, the node I'm adding to my list, which is the guy I built up here. That make sense? So let me visually trace this for you so you see us go through this while loop at least once for the next node we add in. So I set curnode's next node to this guy. Now I'm adding this node to the end of my list. Fair enough. So I call add end. It's going to create me a brand new node, store that in a variable called n. That's that node right there. Then I need to go to the last node of my list. The first thing I say is, does head point to null? It does not. Head points to a real place in this list. So now we need to find the end of the list. So I create another variable called curnode. I make this guy point to the same thing that head points to. So curnode and head both point to this very first node. Then I get into a while loop that says while curnode's next node is not equal to null. So is it true right now that curnode, which is this guy, that his next node is not null? Is that a true statement?
Yep.
He points to a real node right now. So it is true that it is not equal to null. So I'm going to set curnode equal to curnode's next node. I change the value of curnode to be equal to his own next node. So now curnode points there. Spin back up on my loop. Is it true that curnode's next node does not point to null? That's false. Curnode's next node currently does point to null. Is it true that curnode is currently pointing at the end of the list? It is. So what do? I set curnode's next node. I set curnode's next node equal to n. See how that's working? Okay. So that's add end. Add end will let us add plenty of things to our list. So kind of to mimic this, I'll go ahead and say ll.addEnd, what are my things, 374, 3, 7, 4. I run it, it's going to say empty list because when I displayed it was before I added anything. So then I added a 3 to the end, then I added a 7 after that, then I added a 4 after that. So we have to go finish our display method. In our display method, we have an else. What if head's not equal to null? Well, we're going to do something pretty similar to what we did down here, this while loop. I'll steal part of that code at least now. So we're going to create a node called curnode that'll start off the beginning of the list. While curnode's next node is not equal to null, we'll go ahead and we want to display curnode first. Then we want to move on to the next node. So how do I display a node? Well, we probably want to display it in terms of its payload. So I'll go ahead and give myself a quick getter. Source, generate getters and setters. I'll give myself a get for my payload. All right. Now that I have that, inside linked list, I can say system.out.print. I won't kick it down a line. I'll say curnode.getPayload, and I'll concatenate onto that a little arrow-looking thing, kind of a pointer. Looks like a linked list. Get it? Okay. And then I'll move curnode down the list. When all is said and done, we'll do a system.out.println. And just to show we're at the end, I'll just do a little null, which is the end of the list. Okay, so we're walking the list just like we did before, except each time through we're printing out the payload that is inside of kernode before kernode gets set to the next node. So now inside of driver, I can say ll.display, and I'll see my new list, which should be the list 3 linked to a 7 linked to a 4. Oh. I did add 4 to the end, right? I'm not going through the list enough times. Oh, what I need to do is I need to do this. Because the next node of 4 is null, so I'm not getting out here and doing this. So I need to go ahead and then get the final value of kernode.getPayload, concatenate that on with our arrow, and then null. Okay, it was skipping the 4 because this was false that very last time through. Now it'll print out our whole list. 3 to 7, 7 to 4, 4 to null. Make sense? All right, so for your homework assignment, and I'll give you node and linked list as starting points, I want you to write add front. So instead of adding to the end of the list, we're always adding to the front of the list. Okay? We can do both. So I've already done the add end. Now you need to write the version that always adds to the front. It's easier than add end. All right? That's due on Tuesday. And I'll put this code up on Angel for you.